Hello everyone. In this video, we will continue talking about golden section search. We will talk about how to implement this method in MATLAB. Let's see example 1. Find an approximation to the minimum of a function fx, and fx is equal to x times x minus 1. We start with the interval from 0 to 2 and then iterate until the width of the interval is less than 0.01. And it asks you to write the code in the main file and then create a separate function file called golden section.m. Just for your information, I copied the iteration process here. So you can see the formula, how to define C1 and C2 and these 3 different scenarios. You may need this information when you do the coding. So first, let's create a main file. Okay, so we need to first clear the screen and clear all, close all, and format long. In the main file, we need to define the function and then first the initial interval and epsilon step, and then call the function golden section. So let's first define the function f, which is equal to at x times x minus 1. And the initial interval from a to b, a is 0, b is 2. And the epsilon step is equal to 0.01. Then we need to call the function golden section .m. So this gives us the minimum golden section, and the input parameter is the function, the initial interval a and b, and the epsilon step. Okay, note that when we find the mean here, this output parameter mean is the x value corresponds to the minimum of the function. It's not the y value at the minimum. Okay, so we call this file main file. And then we create a function file golden section.m. So the first line will be function, the output parameter mean is equal to golden section, and the input parameter is the function a and b and epsilon step. All right. Before we start to write the content of the function, we need to define the golden ratio, because we need to use that value when we use the golden section method. So we need to define the constant phi. So phi can be defined as 1.618, or you can define it more accurately by using the formula 1 plus the square root of 5 and then divided by 2. 1 plus square root of 5 and divided by 2. Okay, so the halting condition is that when the width of the interval is less than 0.01. So we can use a while loop to control the iteration process. So the iteration process will stop when the width is less than epsilon step. So for the while loop, we need to continue the iteration process when it's the opposite of the halting condition, which means when b minus 1 is larger than or equal to epsilon step. All right. If that happens, we continue the iteration process. So for the iteration process, we first need to find the 2 interior points, C1 and C2. So the formula for C1 is phi minus 1 times A and plus 2 minus phi and times B, right? So it's phi minus 1 times A, then plus 2 minus phi times B. And C2 is equal to phi minus 1 times B and plus 2 minus 5 times A. So this is how to define C1 and C2. So after that, we have 3 different scenarios. The first one is FC1 is equal to FC2. If that happens, we have to halt because we can't continue searching because we don't know where the minimum will be located, right? So we will send an error message to the user. If FC1 is exactly equal to FC2, then we send an error message to the user, ask them to change the initial interval or to change to another method, right? So you need to change initial interval. Because this method, it belongs to the bracketing method, so by using this method, if you start with the correct initial interval, there is a guarantee that you can always find the minimum. So the method is very reliable. It's just that you need to change the initial interval. Okay, so else if the second scenario is that when FC1 is less than FC2, then the minimum will be located between A and C2. So we need to update the variable B by assigning the value of C2 into the variable B. So if FC1 is less than FC2, then we need to update B by giving the value of C2 to B. The last scenario, if FC1 is larger than FC2, then the minimum will be between C1 and B. So we need to update A by assigning the value of C1 to the variable A. And these are the 3 different scenarios. Then we can end this if condition and end this while loop. Okay, so at the end of the while loop, we find we located the minimum. At the end of the while loop, the width of the interval B minus A is less than epsilon step, but we know that the minimum is somewhere between A and B, but we don't know which point gives us the best evaluation for the minimum, because we are not sure if it's A, B, C1 or C2. So we can compare the function value at these 4 points and then find the best approximation for the minimum. So let's write down the 4 possible points: A, C1, C2, and B. Then we evaluate the function value at these 4 points. We call this FPTS, which is equal to the function value at these 4 points: A, C1, C2, and B. Then we find which one is the minimum. So we can use the built-in function min to find the minimum of these 4 different values. And it gives us 2 different parameters. The first one is the value of this minimum and also the position of this minimum. For example, if the position is 3, which means the third element C2 gives us the minimum amount, then the best evaluation of the minimum will be at C2. So it will be basically the position variable gives us the index of this vector PTS. It shows that which one is the best evaluation for the mean. So then we can return this as the output mean, which is remember that mean is the x value corresponds to the minimum of the function. Okay, so let's save this one as golden section.m. All right, so we can run this file. So I think the output parameter, let's change this minimum. So mean is a built-in function, so we can change the output parameter to a different name. Let's call this mini, and so the output parameter will be mini. Okay, so let's see if this works. Okay, so the mini will be a value close to 1/2, because analytically we know that the minimum of this function x times x minus 1 will be located at 1/2, and our value is close enough within the tolerance to this value, so this works. All right, so this is how to implement golden section method into MATLAB. In the next class, we will talk about a new topic, which is another method for optimization. That method is called Parabolic Interpolation. That method belongs to the open method.